Today on the Perception in Action podcast, revisiting Bernstein's freezing degrees of freedom hypothesis. What evidence is there that it is a movement solution that is used early in learning? Is it universally adopted? What factors might influence if and how it is used? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, I want to revisit a topic I first discussed in episode 94, Bernstein's freezing degrees of freedom hypothesis. In his seminal work on motor learning, Nikolai Bernstein presented both a major problem and a potential solution. Of course, what I'm referring to here is his now famous degrees of freedom problem and the idea of freezing. As I think most people also know, although Bernstein did most of his work in the 1920s and 30s, it didn't really become known to the broader scientific community until it was published in 1967. Despite this delay, Bernstein's ideas have been now accepted as foundational and seminal in motor control and motor learning. To quote an article by Newell and Valancourt, although the Western scientific community was slow to pick up on Bernstein's ideas about the physiology and biomechanics of motor learning and control, it has, in essence, made up for lost time by promoting Bernstein's notion about degrees of freedom as a, if not the, central problem for the field of study. End quote. Given the high status of Bernstein's ideas, it's somewhat surprising how little they've actually been investigated in research studies and not really gone through continued theoretical development. To quote again from the same Newell article, the degrees of freedom issue is regularly restated as a theoretical backdrop or even a central problem for motor learning and control, but there seems to be limited advance beyond Bernstein's ideas. End quote. In terms of research studies, a systematic review by Guillermes and colleagues published earlier in 2020 looked at all of the studies that have tested Bernstein's core ideas of freezing and freeing degrees of freedom. In the 53 years since the ideas were presented to the Western world, how many published research studies have tested them? Guillermes and colleagues identified a grand total of 13. That would basically fill one issue of a journal. By comparison, there are nearly that many studies that have investigated the dress illusion, whether it was black and blue or gold and silver, since it became an internet sensation in 2015. So in today's episode, I want to do a couple things. First, I want to extend the material I presented back in episode 94 by looking in more detail at these 13 studies that tested Bernstein's ideas. What evidence is there that freezing degrees of freedom is a universal strategy adopted by all performers in the early stages of skill acquisition? What factors seem to influence when and if it is used by a performer? After doing that, I want to give some consideration as to why these highly influential ideas haven't really been studied very much and how we might advance them. Part of my motivation for doing this now is that I'm currently writing up a paper where I look at some of these ideas in my baseball training data. So I may talk a little bit about that too. I've talked about the issue of coordinating degrees of freedom many times on the podcast now, but to use Guillermes et al.'s description as a reminder of the issue, quote, "It is important to understand how a system, the human body, with so many independent components, bones, joints, muscles, etc., which have countless combination possibilities, can be controlled by a single effector system, the central nervous system. For Bernstein, the solution to this problem would be mastery over the degrees of freedom, known as the independent components of the control system and the various possibilities of its movement." End quote. Or, as stated in Bernstein's own words, coordination is, quote, "the process of mastering redundant degrees of freedom of the moving body," or in other words, its conversion to a controllable system, end quote. Note here that these quotes reflect the fact that Bernstein was focused on the biomechanical degrees of freedom in movement in terms of the joints and muscles. But as I will discuss in a bit, the degrees of freedom problem actually also applies to other levels of analysis in the system. So that's the problem, controlling the abundant, redundant degrees of freedom. What is the solution? As Bernstein proposed, one of the simplest ways we can solve this problem is that the initial phases of learning a new skill, we could reduce the number of degrees of freedom by quote-unquote freezing them. When you hear that word, it brings to mind immobilizing and not moving part of the body. Obviously, when I keep a body part static while trying to achieve my goal, I no longer need to coordinate its movement, so it's no longer a potential degree of freedom in my movement solution. I've simplified the problem by completely taking it out of the equation. However, this is only one of the types of freezing Bernstein was referring to. Another way I can reduce the problem of coordinating the movement of different parts of my body is by temporarily linking or coupling one body part to another. So the body part is not completely immobile, but is no longer a degree of freedom in my movement solution because by definition, it's just doing whatever the body part it's coupled to is doing. I have again simplified the problem by reducing the number of options I have on how to move. Consider learning to serve a volleyball underhand. An example of Bernstein's degrees of freedom problem in this situation is how do you coordinate the rotation of the arm around the shoulder joint, the rotation of the forearm around the elbow joint, and the rotation of the hand around the wrist when striking the ball. An example of Bernstein's first type of freezing would be if you perform the serve with your arm completely straight and locked the entire time. So you're simplifying coordination by keeping the elbow and wrist joint immobilized and removing them as possible degrees of freedom. An example of Bernstein's second type of freezing would be to have the forearm bend around the elbow joint during the motion, but doing so that the rate of rotation around the joint was the same for the shoulder and the elbow. Another key idea within Bernstein's proposal is that these freezing solutions are non-optimal, so that we should expect them to be only used early in skill acquisition. With more practice and more proficiency at the task, we should expect a freeing of degrees of freedom, so that the performer can switch to other, more effective movement solutions. How have Bernstein's two types of freezing been quantified in research studies? For the first type of freezing, the primary measure that has been used is the joint range of motion. The basic prediction is that if Bernstein's freezing to freeing progression is what occurs, then the joint range of motion should be larger after training than it was at the start of training. For the second type of freezing, the main dependent measure that has been used is joint cross-correlation. A cross-correlation between joints is a measure of the similarity between the time series of the two joint angles during a movement, with a value of 0 indicating that the increase or decrease in the angles during the movement is occurring independently, with a value of 1 indicating they are changing in the same way or dependent on each other. Thus, again, if Bernstein's hypothesis is correct, we should see a high value of cross-correlation near -1 or 1 at the start of training, with this value moving towards 0 post-training. So let's look at the evidence for Bernstein's ideas from research studies that have used these two measures. As I mentioned, in their systematic review, Guillermes and colleagues identified 13 training studies that have used joint range of motion and/or cross-correlation to assess the freeing degrees of freedom hypothesis. The first studies were published in 1989, and there hasn't been a new one since 2013. The sports skills that have been investigated include simulated skiing, soccer kicking and passing, darts, and racquetball. There have also been a couple studies that have investigated more general skills related to balance. An issue that needs to be addressed in future studies in this area is that only one of these 13 studies used a sample size greater than 10 participants. What has been found? Let's first look at studies using joint range of motion as the measure. By my count, 6 out of the 8 studies that use this measure found the predicted pattern. That is, lower values for joint range of motion at the beginning of training, getting larger as the number of practice hours increases. I already discussed a couple of these studies, including the ski simulator study by Varakin and colleagues and the soccer study by Hodges and colleagues back in episode 94. So let's look at one I didn't discuss. In a study published in 2001, Smith and colleagues examined changes in the joint range of motion for 10 novices learning to perform a forehand stroke in racquetball. After 5 days of training, the range of motion of the pelvis increased from 31 to 48 degrees, and the range of motion of the upper torso increased from 58 to 80 degrees. There were no significant changes in the elbow, which increased by about 5 degrees, or the wrist, which increased by about 7 from pre to post training. This is a very similar pattern to most of the other studies that have looked at joint ranges of motion. So, a couple things to note here. First, freezing and freeing does not occur for all joints. There are going to be some ranges of motion that don't change at all during learning. Second, it is not the case that the joint is completely immobilized in early learning, i.e., the joint range of motion is not zero at the start of training. An important issue that Newell and Valancourt raise in their article is that this joint range of motion evidence is really just indirect and descriptive and does not really test the heart of Bernstein's ideas. Freezing is a coordination solution that helps performance in the short term, while it is assumed that increasing the joint range of motion reflects the release and exploration of a higher number of degrees of freedom. But simply showing that the range of motion for different joints are lower at the start than get bigger by the end of training does not provide direct evidence that this is a coordination solution being adopted by the performer to reduce the degrees of freedom. It's a similar problem in a way to just assessing skill by looking at overall movement variability. By just looking at individual measures, you're not getting to the heart of the problem that Bernstein raised, the coordination of multiple things. Now let's look at the one study that didn't find the predicted pattern. In a study published in 2013, Coe and colleagues tested Bernstein's freezing-freeing progression by measuring joint ranges of motion for 6 participants that learned to balance on a moving platform. They found the exact opposite pattern to the other studies. Specifically, during the early phase of trials, all joints exhibited large ranges of angular motion that tended to decrease with practice. So in other words, if a lower joint range of motion is indicative of freezing, it was occurring later, not earlier in practice for this task. I will return to this discrepancy in a moment, but first I want to look at studies that have measured the cross-correlations between joints. Remember, when we're talking about cross-correlations, values near 1 or -1 reflect a coupling or dependence between joints, with 1 indicating the joints moved in phase and -1 indicating they're moving out of phase, while a value closer to 0 indicates greater independence. Therefore, based on Bernstein's hypothesis, we should see values of cross-correlation moving closer to 0 as the number of practice hours increases. A value approaching 0 is again thought to be indicative of freeing control to make more degrees of freedom available for the coordination solution. 6 out of 8 of the studies that used this metric found the predicted pattern. I talked about a couple of these back in episode 94. For example, in the Verreiken study of learning to ski on a simulator, the cross-correlation between the ankle and hip was roughly 0.7 at the start of training and decreased systematically to roughly 0.3 after 25 trials. While in the Hodges et al. Study of passing a soccer ball, the hip-knee correlation was roughly 0 at the start of training, decreased to -0.8 after 5 days, then went back up to -0.1 over the next 5 days of training, suggesting a pattern of freezing, then freeing degrees of freedom. What about the studies that didn't find this pattern? In a study also examining soccer, Chow and colleagues found large individual differences in the patterns of cross-correlation across practice, with some participants showing the exact opposite pattern to that predicted by Bernstein's hypothesis. For example, for one of the participants, the knee-ankle cross-correlation was near 0 at the start of training and then increased roughly monotonically up to a value near 1 over the 12 training sessions. So overall, 10 of the 13 studies in this systematic review provided evidence consistent with Bernstein's hypothesized strategy of freezing degrees of freedom early in learning, then freeing degrees of freedom with more practice. This has been shown by either lower values of joint range of motion or higher cross-correlation between joints. However, 3 studies have provided evidence inconsistent with this hypothesis. 2 of these studies found the exact opposite pattern to the predicted pattern, that is, an increased coupling between joints with practice, while 1 found no significant changes. It is also worth noting that even in the studies that did support Bernstein's ideas, there's not always a simple linear change in available degrees of freedom across practice trials. While some showed a monotonic decrease in cross-correlation, for example, others showed an initial increase followed by a decrease. So what can we make of all this? In their paper, Guillermes and colleagues propose that this inconsistency in the findings is due to differences in the nature of the task being used. First, in looking at the type of task, they note that 6 studies investigated continuous tasks, like skiing or balance, while 7 studies investigated discrete tasks, like darts or soccer chipping. 5 out of 6 of the continuous tasks and 5 out of 7 of the discrete tasks supported the freezing to freeing hypothesis, so no real pattern there. But what did seem to matter was the interaction between task type and task objective. For some of the tasks, accuracy was emphasized, while for others, velocity was. Two of the studies that provided inconsistent evidence were discrete tasks that emphasize accuracy, leading the authors to conclude, quote, "Therefore, there seems to be a relationship between the objective to be reached and the practice skill class, which could influence the degrees of freedom freezing and release at the beginning of learning. These two studies suggest that when the objective of a discrete skill is movement accuracy, freezing the degrees of freedom throughout the learning process to gain precision could be the strategy to explore. On the other hand, if the objective of the discrete skill is maximum velocity production, releasing the degrees of freedom during learning could be the selective strategy to ensure greater ball velocity." End quote. For me, this idea again points to a key issue that needs to be addressed in this area. That is, establishing a more direct connection between coordination and performance in these studies. What is the purpose of freezing? Is it simplifying the problem? In what way exactly? Or is it, as the authors suggest, a way to increase the precision of movement? Another important point the authors touch on briefly, that has been raised by Newell several times in his papers, is the stage of learning participants begin at in these studies. For most of these tasks, like balancing, throwing, etc., participants are not complete novices, nor do we use enough practice trials in the study to let them become truly elite at the task. To quote Newell, "Most studies of human motor learning have been focused on and are essentially limited to an intermediate stage of non-optimal control. As a consequence, only a few motor learning experiments have examined either the early stage in which a new coordination mode is established or the final stage that is related to the optimization of performance." End quote. In other words, given that freezing is a strategy Bernstein proposed would be used very early in learning, it is perhaps not surprising there's not a lot of consistency in the research evidence, because in many studies we've essentially missed this stage. So where do we stand in terms of Bernstein's seminal freezing-freeing hypothesis? Well, I think Newell and Valancourt hit the nail on the head in identifying a key way that we need to change our thinking about this. Quote, "The second open issue is whether freezing the degrees of freedom is a universal learning strategy, or is rather a constraint-dependent consequence of reorganizing the degrees of freedom to realize a new task goal. The viewpoint we subsequently develop here is that the combined notions of initially freezing and releasing degrees of freedom are constraint and in particular task-dependent, and not general directional stage-like strategies of learning to harness the degrees of freedom." End quote. So in other words, just like everything else we see with self-organization and learning, the coordination pattern that emerges depends on the interacting constraints faced by the performer. We should not expect to see a simple linear pattern of freezing and freeing degrees of freedom for all performers. As shown from the Guillermo's and colleagues' review, how the problem of coordination is solved depends on the task constraints. Another factor that affects this process is the structure of practice. In a study published by Lee and colleagues in 2014, a linear instruction method using prescriptive repetitive drills was compared to a nonlinear method, manipulation of task constraints including the equipment and the rules. It was found that even though there were no differences in performance at the end of training, the nonlinear training group showed greater movement variability and a greater number of movement patterns after practice. I have found similar things in the recent analysis I've been doing for a paper I'm writing up. Using the data from my 2017 training study, I found that the VE adaptive group, which experienced a higher level of variability in the pitch type, location, and speed in practice as compared to traditional batting practice, showed more evidence of freeing degrees of freedom. Another factor that matters in all of this is, of course, the individual constraints of the performer. In my analysis, I've also been finding that batters who could generate a higher bat speed at the beginning of training are more able to take advantage of the available degrees of freedom and have a higher level of good variability. Again, all of this is nicely summed up in a quote by Newell. The central point arising is that the pathways of organizational change in learning are not limited to an increase in the number of biomechanical degrees of freedom as proposed by Bernstein, or a decrease in the dynamical degrees of freedom as proposed by Mitra et al. Rather, there can be either an increase or decrease both in the number of involved mechanical degrees of freedom and in the dimension of the attractor dynamic of the motor output. In either frame of reference, the direction and specifics of the changes are dependent on the confluence of constraints in action." End quote. So in sum, Bernstein's concept of freezing degrees of freedom is still a very valuable idea, but how, when, and if it is used depends on the constraints involved. The initial freezing and the speed and nature of the release of degrees of freedom will not be the same for all performers and in all situations. Much more research is needed to understand how constraints influence coordination early in learning. Another issue we really need to investigate more is what happens after the freezing-freeing progression. That is, how do functional couplings between degrees of freedom and coordinative structures develop? To again quote Newell, "Even within a strategy of increasing the degrees of freedom, it is an open issue as to whether all restrictions are lifted, as suggested by Bernstein, or whether it is all restrictions consistent with a controlled coordination solution. In summary, we have little understanding of the search strategies that are used to change the number of degrees of freedom independently regulated in the coordination solution and the specific role of task constraints in this process." End quote. More on this coming soon. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.